Neuroscience and AI are intimately connected and have been really since the advent of artificial intelligence. One major strand of AI research, artificial neural networks, was originally very directly inspired by the way that neurons process information in the brain. And these artificial neural networks have been a mainstay of artificial intelligence for a really long time. And although the more recent developments in AI don't so directly copy brain structure like artificial neural networks did, the brain remains this really important source of inspiration. And one of the more recent technical advancements in AI has been transformers. And this new type of architecture is what has allowed large language model applications, those like ChatGPT that we're all pretty familiar with now. It's what's allowed them to work. Now, Sentry's knowledge tracing model, which is what informs our personalized learning recommendations, it basically is the foundation of Sentry's recommendations and personalization. That knowledge tracing model is a transformer-based model itself. And there are some really interesting similarities in how transformers learn and how human brains learn. And I'm going to give a really brief summary of these similarities and kind of shared characteristics. The first of these is self-attention mechanisms. So self-attention mechanisms in human brains allow us to selectively focus on the most important or the most relevant information that's coming in. This brings a lot of efficiency to how our brains navigate through the world. For example, right now you are hopefully focusing on me on the screen, and your brain is filtering out all of the other visual information it's receiving, all of the other auditory information, you know, the noise out in the corridor or on the street or something that it's receiving. And essentially this is allowing you to focus on what I'm saying and therefore to learn it, understand it more efficiently and effectively than if you were paying all of those other things the same amount of attention that you were paying me. And that self-attention is not effortful. You're hopefully not having to really deliberately filter those extraneous sounds and sights out. Your brain is just doing that automatically. And transformers also utilize a kind of concept of self-attention mechanism. And this is probably one of the biggest aspects of transformers that allowed this really big leap forward in the types of tasks that they can then tackle compared to the earlier neural networks that I mentioned. So the second shared characteristic is hierarchical processing. So in the brain, when information comes in, it's passed through to different areas of the brain sequentially to process that information at increasing levels of complexity, right? So for example, staying with an example of visual processing, where the first areas of the brain that the visual input passes to are used for really simple categorization and processing, such as detecting color or motion, when we get to more complex scenes or things like processing faces, which are really important for the brain to be able to decipher and understand, that signal is going to be passed through maybe 6 or 7 different regions. And at each stage, the processing becomes more abstract. And importantly, it utilizes the output from that earlier stage. So if you're looking at a face, the brain just doesn't go immediately to the 6th or the 7th region. It has to go through each stage. And if you're looking at something simpler, it doesn't go through all of those stages. So you can see that there's already a real efficiency in that processing. Transformers have this similar principle of these sort of stacked layers that also progressively extract higher level features from the input they're given, which is the output from the previous layer. The third shared characteristic that I want to talk about is distributed representation. And in a way, you could think of this as your brain not putting all its eggs in one basket, right? The brain kind of shares out the important tasks it has to do across the brain. And this provides resilience and flexibility. We know about this from brain damage studies, right? Where, for example, after a mild or moderate stroke, where there's localized damage to a specific area, we may see impaired function, for example, weakness in a certain part of the body. But rarely do we see from a mild or moderate stroke total loss of function, as in no movement in that body part at all. And when we do see total loss of function over an extended period of time, this is typically due to much more widespread, a really serious stroke or a really serious brain injury that's damaging multiple regions of the brain. And transformers also use this kind of distributed representation across their networks for efficiency, robustness, flexibility, exactly like the brain does. And what's really important about distributed representation in learning is not just that if someone suffers from a stroke or other brain injury that they will be able to recover, although of course that's very important, but it means that the areas of the brain or the areas of the transformer can work together to complete tasks, again bringing this idea of efficiency and efficacy to the learning so that we can learn more things more quickly and more effectively. So those are the three shared characteristics between transformers and brains, ways that transformers have been really inspired by how the brain learns. We've had self-attention mechanism, hierarchical processing, and distributed representation.